Thank you for the introduction, and it's a real pleasure to be here. I'm going to talk about silicon photonics, which is a young field, and it's completely exploded in the past decade. So what is silicon photonics? It's the idea that you could guide light not in fibers, not in lithium niobate, not in any of the material that we're all used to, but to guide light on a silicon chip fabricated in a microelectronic industry, nothing to do with optics. So this field started just early 2000, not too long ago, and I can still remember talking about these ideas and seeing people literally rolling their eyes and basically saying, what is she talking about? Silicon is never going to be an optical material as good as all the other materials that we're all used to. And today, there are products after products being announced based on silicon photonics. So it's extremely excited time to be in this field. So in the early 2000s, the microelectronic industry was desperate. It was becoming clearer and clearer that the bottleneck for the microelectronic industry and for computing in general is power dissipation. And we actually know that. I mean, most data centers, they are all located next to rivers, in cold places, so that's not new, we know that. Actually, if you open your own personal computer and you turn off the fan, you could cook an egg. But optics could alleviate that, and I'll tell you a little bit why. The reason why the power dissipation problem exists, the whole generating heat issue is there, is not because of computing. Actually, it has nothing to do with computing. It has everything to do with transferring data from one point to another. Say, for example, transferring data between two different processors or between a processor and a memory, not the computing. Transferring all this amount of data over relatively long distances, several centimeters, that's what consumes power. And optics can do that with no problem. We know that from telecom. So in the early 2000s, the whole microelectronic industry and lots of government agencies, they all stood up behind this idea, and they started throwing money on this topic. They wanted to make silicon, instead of an electronic material, an optical material. So why this is so hard? So what's hard about transferring data on a silicon chip as opposed to over optics, as opposed to over copper, for example? So the first challenge is simply the fact that those silicon waveguides, or those basically miniaturized fibers, but now they're all on a chip, are tiny, are just a few hundred nanometers. And because they're so small, how are you going to actually get light in and out of these waveguides? That was a major challenge in the beginning of the 2000s. And here I'm not even drawing it to scale. So you have this huge fiber, you have this tiny little waveguide, and you're trying to get light in and out of this little waveguide. And if you actually just butt couple, put them one against another, you're going to get just a few % through. So my group, as well as several other groups, we all started working on this topic. And I should say there was beautiful work done by NTT and IBM and MIT on this topic. What my group demonstrated is the fact that you could actually take a waveguide And in order to make light go seamlessly between the fiber and the waveguide, the only thing you need to do is take that little waveguide and make it even smaller. Make it much smaller than the wavelength. So now you take that little waveguide, you have this little needle, you point it towards the fiber, and magically all the light goes seamlessly between the fiber and the waveguide. And that's because what you're doing, you're basically delocalizing the mode. You're building a mode out of that little needle that looks like the one of a fiber. So you have perfect matching. And that idea was a little bit weird to use an inverse taper. We call it inverse because it's a little counterintuitive at that time. But today, this is one of the major building blocks of silicon photonics, and most silicon photonics groups rely in some way or another based on this inverse taper. The second problem that we all had to face with on trying to work with silicon as an optical material was the fact that silicon doesn't have an electro-optic coefficient, meaning I cannot change the optical properties of silicon by applying voltage. That's a major problem because remember the whole vision here was to propagate data over optics. So I have my 1s and 0 volts, and I need to translate them into yes light, no light. So that was a major limitation. And that's actually fundamental. Silicon is a centrosymmetric material. It doesn't have an electro-optic coefficient. Fundamental. So in the years 2003, 2004, there were several groups working on this topic, on trying to make silicon react to light, basically react to voltage. So we wanted to change the optical properties by applying an electric field. So the idea that my group demonstrated, I should say that in parallel to our demonstration, there were beautiful demonstrations by Intel and by Luxtera and by several other groups. But what my group demonstrated was the fact that you could inject carriers or extract carriers, just electrons and holes, and on average, you're going to change a little bit the index of diffraction. You're actually going to change the index of diffraction by tiny, tiny bit, by 0.01%. But it's okay. You can use that to get amazingly efficient modulation. And you get this efficient modulation by putting those carriers inside a little cavity. So the cavity amplifies the effect. You put light in the cavity, let light circulate there, and only then get it out. So the actual cavity that we use is these little waveguides. So you're looking from the top, light is propagating from the bottom, and the cavity is just a circular waveguide. So that black circle is our cavity. And those blue and yellow areas are the diodes. These are the ones responsible for changing the electrons and hole concentration. So what you see here is light going in, goes into this circle, stays there for a long time where carriers are injected or extracted, and only then it gets out. And it works beautifully. Today, there are gorgeous modulators that work at 50 gigahertz. People have taken these ideas and pushed them much farther than we could all have dreamed of. Here, the beautiful work by Michael Watts at MIT, by Reed in the UK, and there are many, many groups that have demonstrated tens of gigahertz modulators. That's incredible, because 10 years ago, we were all at loss with the fact that silicon doesn't have an electro-optic coefficient. And today, we have modulators that perform even better than the traditional modulators based on completely standard optical materials, like, for example, lithium niobate. So because of these advances of the electro-optic materials and the fact that we know now how to interface between fibers and waveguides, and we know how to make waveguides and components in general that perform amazingly well, very, very small optical losses, the field exploded. And in just a few years, it went from ideas on paper to products on the market. Just in 2016, the year hasn't ended yet, there were announcement after announcement on products based on silicon photonics. That's unbelievable. Silicon photonics is the field that perhaps grew the fastest in less than 10 years. Perhaps maybe besides Giant Magnetoresistance that actually got the Nobel Prize in 2007, this is the field that grew the fastest. So is silicon photonics scalable? Meaning, can we continue growing the bandwidth? And well, the first thing you could say, yeah, I mean, you could just do what we all do in telecom. You could do WDM, waveless division multiplexing. So use all these modulators and the waveguide that I showed you and propagate different colors. And that was the vision of silicon photonics. But there is a catch. If you want to do what I'm plotting on the top, this WDM idea, this lots of lasers with lots of modulators, you pay a price, and the price is power. There have been beautiful lasers that have been developed for silicon photonics by Bauer's group and Royal Butt's group and Intel's group. But it actually, the power dissipation due to lasers have nothing to do with which laser you use. Lasers in general consume power, and it has mostly to do with the drivers, with the stabilization, with the temperature stabilization. That's pretty fundamental. So if you want to increase the bandwidth, you do need to pay the price of bandwidth scalability. So it would be nice to think about ideas that would enable us to increase the bandwidth without paying such a high price. So we want to decrease the number of lasers that we want and still enable to grow in bandwidth. So my group is working on two ideas to push this bandwidth without paying the price. And the first idea is, how do we get modulators running not at 10, not at 20, not at even 50 gigahertz, but say at hundreds of gigahertz? And that could be with a single laser. But there are not many materials that can actually run at hundreds of gigahertz. And definitely not many materials that are compatible with silicon. But there is one, and that's graphene. Graphene is actually completely compatible with silicon. There are products made by Samsung that actually are integrated part of the back end of silicon, so now that it's done on a massive scale. And it has amazing mobility that could enable you to change the optical properties at speeds of hundreds of gigahertz. And you could just put it on top of your waveguide. Just design it so that light interacts very strongly with the material. And it turns out that if you apply a field over these graphene layers, you change the optical properties not by 0.01% like we had in silicon, but by 100%. 100%. So you might say, yes, but it's one monolayer. And my mode is much larger than that. That's not a problem. The cross-section is so strong, the optical cross-section is so strong that if you just place the layers, you can see these little purple and black lines, these are the graphene layers, on top of the little waveguide. In this case, it's a silicon photonics waveguide based on silicon nitride. Light actually sees a lot of what's laying on top. So you change a little bit the optical properties of the mode by applying the field on the graphene, and it turns out that this is almost an order of magnitude stronger than what you can do in silicon, and fundamentally, it could be at hundreds of gigahertz. We've just demonstrated these devices running at tens of gigahertz, and right now they're only limited by our contacts, but in principle, they should be running at hundreds of gigahertz. So we're very excited about this process. Told you there are two ideas on how to actually scale the bandwidth without paying the price of the power dissipation of lasers. And the second idea is using not waveless division multiplexing, but mode multiplexing. So in a waveguide, we can have many modes. And that's very similar to what we all thought in fibers. There was extensive work done on fiber on trying to mode multiplex, meaning sending information on the different modes. They are, by definition, orthogonal, so you could propagate all these modes with different information, just like we do with waveless division multiplexing on a single waveguide. But in fibers, once you send light into one of those modes, they will mix. They actually, in fibers, all these modes are very, very similar. But in those waveguides, in those silicon waveguides, it's a completely different ballgame. Those modes are very different. Once you send light into one of those modes, it stays there. Very difficult for it to actually mix with the different modes. And there were beautiful theoretical work that actually showed that you can extract a specific mode and feed a specific mode. And we can do that now. My group actually demonstrated the ability to put in just a specific mode, say just the third order mode inside the waveguide, and get just a different mode, say just second order mode, and all of them were able to feed in hundreds of, tens of gigabit per second on each one of those modes. So in principle, one could take these ideas of spatial mode multiplexing and combine it with very, very fast modulators and achieve extremely high bandwidth with very few numbers of lasers. Okay, so what's next for silicon photonics? So silicon photonics enables you to take extremely complex systems based on, for example, splitters, fibers, lenses, systems that look like that. Very messy system. And miniaturize them, integrate it on a chip. And that's the reason why silicon photonics is now introduced in all different areas. This is one example, it being introduced in quantum optics. It's also being introduced now in neuroscience. And neuroscience is actually a very interesting idea. In neuroscience, we know that light can actually activate specific neurons. And that's a relatively new idea, about 10 years old. That's the field of optogenetics. And the way it's done today in most neuroscience labs, you introduce a huge fiber into the brain of the mice. the fiber is pretty detrimental to the tissue. And once the fiber is there, it activates the neurons, but it activates all the neurons that over its cross-section. So it's a pretty large area. I don't want that. What we all would like is to put into the brain of the mice tiny little needles, silicon photonic needles, that wouldn't be detrimental to the brain. And from outside, using switches, modulators, and so on, control where exactly light is going into the brain, which neuron is activating. So there are several groups now working on this, including my own group. So these examples, together with the examples of the work in quantum optics that Jeremy O'Brien was actually one of the pioneers in this field. These are examples of fields that actually take very complex systems and large systems and miniaturize them. But we actually can do better. We cannot just miniaturize. We can actually change the way light propagates. We can change the group velocity dispersion. We can change the gradient field. We can change the actual local intensity of light in these silicon photonic waveguides. And these properties can be completely different than the ones that we are used to with traditional optics. And just to show you the power of this technology, I'm going to show you the effect that silicon photonics had on nonlinear optics. So when you think about the nonlinear optic lab, you think about very large, powerful laser. It turns out that using silicon photonics, you can do nonlinear optics with just a laser pointer. So why is that? Silicon photonics, of course, it localizes light in very small locations, so the effective nonlinear effect is very strong. But most importantly, silicon photonics enables you to actually dial in the dispersion of light, the group velocity dispersion. And that's a must if you want to do nonlinear optics over large bandwidth. So if, for example, you take 4-wave mixing, just one example of a nonlinear parametric process, you're basically trying to mix waves with completely different wavelengths. And usually, you are limited in bandwidth by the dispersion of the material. And that dispersion is given by nature. And it turns out in silicon-based material, the dispersion is pretty strong. But we don't have to live with the dispersion that is given us by nature. We can design dispersion of these waveguides, and you can see here the plot on the left that shows how much the index changes for a single shape of a waveguide with frequency. This is a very strong effect. It's a waveguide dispersion, has nothing to do with the material. This is a dispersion that is given you just by engineering the mode of the waveguide. And it turns out that this dispersion can completely counteract the dispersion of the material. So if you don't like the dispersion that nature is giving you, no problem. You can counteract with by dialing in this dispersion, by designing the waveguide. And my group, together with Alex Gaeta's group, demonstrated these waveguides in 2006, this ability to tailor this dispersion. So based on this dispersion effect and the ability to propagate light with very low loss, I mean, you can make cavities based on silicon photonics that have extremely high quality factor, very, very low loss. You can combine them to demonstrate a parametric processes that need pumping power of just microwatts. So these are microcombs, these are optical combs generated on a silicon chip. You basically come in with a CW pump, just a single wavelength CW, very low power. You send it into your little cavity. This cavity is similar to the one I showed you before. And you generate a whole range of wavelengths that are all phase locked. So I should say the pioneer in this idea of generating these optical comb, phase-locked optical combs, was Tobias Kippenberg. By using, there he used discrete components based on glass, and now we can actually do this on a silicon chip, and this was work by my group together with Alex's group in 2010. And this field now completely exploded, these microcombs, because you can apply this to sensing, to metrology. There's a whole field, to spectroscopy. There's a whole range of applications. You could envision the holy grail of sensing, where you would have a pocket-sized, tiny little device that could remotely sense fingerprint, molecular fingerprint. That's one of the holy grails of sensing, and we can now actually do that using these microcombs. And that's because these microcombs, based on silicon photonics now, are being generated all the way from the UV down to the mid-IR, and they were demonstrated by many groups now working on this in this area. So silicon photonics originally started as a motivation from datacom or telecom. So trying to push information without paying the price of power dissipation. But today, it went much farther. Today, silicon photonics is now applied to a whole range of fields. It is applied to fields that almost have nothing to do with optics, like neuroscience, fluidics, mechanics. I feel extremely grateful to be in a field that actually went from ideas on paper to actual products and can actually inspire ideas in fields way beyond the one that we are working on right now. I want to thank all the people who actually did the work, and you can see here from the professor and doctor, these are all alumni from the group. And I also want to thank the group of Alex Gaeta, who did the work in nonlinear optics with our group, and Professor Karen Bergman, who did the work on multimode multiplexing, did quite a lot of measurements on these systems. Thank you.